So today's session is on how can we leverage Simsolid uh, for using for evaluating your structures for dynamic and thermal loads, right? So before seeing that, let us see what is the importance of dynamic simulations, right? So dynamic simulations plays an importance in mostly engineering organizations for various reasons, right? So what are the crucial key aspects considered? Like, so if you start from the performance evaluation, especially when the structure is undergoing the G loads or vibrating loads, right? While evaluating the performance of the structures, those needs to be considered. And the same way for virtual prototyping and parameter optimization, right? So for this, how can we do the dynamic simulations in the Simsolid? So Simsolid actually uses a modal decomposition approach for simulating the dynamic runs. So which is supported by high accuracy model solver, which can solve even a large assemblies. If you have 1,000+ parts, it can be solved in a matter of minutes. Even for the geometries, including with thick or thin, or even with big or small parts. So you can do the frequency response simulation or transient response, even the random response simulation, and the recently added simulation like squeak and rattle. So let us see in detail what these are all for. So in the frequency response and transient response, typical applications may be like for mostly on NVH analysis of vehicles. It can be rotating machinery or transmissions or powertrain systems, right? So whenever we do the transient or frequency response simulation, you need to have first modal results, so which is taken as a reference for simulating this response. Okay, that's where, and also you need to set up the parameters and time functions and the dynamic loads. So, and you can, as the analysis is fast, you can plot your time domain if you're going for transient, or you can plot frequency domain plots if you're going with the frequency response. Okay, so you can also do the random response simulation, where mostly if you have any testing data where your vehicle has run on the road, different road surfaces. So right, so the road load data or something. So those things can be used as an input for your random simulations, and you can also plot your responses versus the frequency animation, and also you can plot XY frequency domain plots. Okay, and then in the dynamics we do have squeak and rattle uh, simulation, where this basically is caused by the relative displacement between the two parts, right, which are mounted with or without any gap, which can happen in a very short duration of time. So when we say the rattle, it means basically relative motion between the components which come in contact for a short duration of time due to the impact forces. So rattle generally occurs when the components are loose or overly flexed, whereas squeak is an undesirable sound which occurs when two surfaces interact with stick or slip phenomena, and the friction is caused by the relative motion between the surfaces. So here the frictional energy is stored in the contact surfaces and is released when it exceeds the kinetic friction. So which in turn produces an audible squeak. So we can identify these things by giving we need to specify the tolerances, like gap tolerance of open and close for rattle, and stick slip is for a squeak. Okay, so these the input you need to specify, and also the prerequisite for it is you need to have a transient dynamic run already run, which you need to specify, give it as a reference to solve this. Okay, and then we'll be seeing on the thermal simulation also. So thermal simulation also plays a crucial role in various engineering organizations, because this actually provide how heat is generated, transferred, or dissipated within the systems and components, right? So you can perform heat transfer simulations for conduction and convection for now. Uh, so the radiation, for now, we don't have this. So we can perform thermal steady state simulations. If you have any imported loads, thermal loads, you can import it and do the thermal simulations on it. You can also perform transient thermal simulation. These also recently added enhancement in the Simsolid. And you can also couple the structural and thermal simulations and evaluate the performance of the structures. Okay. So let us move on to the demo. Uh, in the last week also we had a session on the Simsolid on the fatigue side. So today also we are seeing on the automotive chassis. So for evaluating the chassis design, so the what are the simulations which play crucial role in evaluating this? So first is the stiffness evaluation, and then comes vibration and thermal, right? So today we'll be seeing on how can we perform the vibration, that is FRA for transient response on the chassis model, and also we can evaluate the thermal simulation on that structure. Okay, and the fatigue one we have already saw this in our last session, that is on July 26th. If you have not attended, you can have the recording of it, which is available. So let us move on to the directly the demo. Yeah, so this is a chassis model. So for this, I have already done the initial, uh, given the connections and the initial linear static run of on it. So here you can see the results. And then I have done the modal analysis on this chassis. So you can see, we'll just review the results of mode shapes. Okay. So since the dynamic runs in the Simsolid are based on the modal approach, so we need to have the modal results first before doing that. So let us go to, first we'll do the frequency response. So while setting up, we need to link the modal run, and also we need to select the frequency span from which frequency to which frequency you want to perform. So maybe upper limit I can take till 6 modes. Okay, so I'll be taking this, and the damping ratios you can specify over here, or you can you can carry on with the default damping ratios, or you can go with this. You can specify this F1 and F2, and you can go with this damping values. So right now I'm going with the default damping ratios. And before setting up, yeah, you can activate this so that while evaluating, while solving, it checks the peak responses, like at what frequencies the peak results are coming. Okay, so those things you can get by activating this. And just say okay. So once we are given the setup, we need to specify, as we are going with the frequency response, right? So we need to specify frequency function, where we'll be giving the curve. So here either we can have a .csv file, frequency versus amplitude factor, or we can go with the standard. So in the standard function type, we have triangle or rectangle or half sign, where you need to specify the amplitude and what is the start frequency and what is the span. So those things you need to specify for it. So right now I'll be going with by importing. Suppose I'm importing this data of frequency versus amplitude factor. Okay. So now I have imported the curve. So now we'll have load. So excitation load. So I will be applying the excitation load on the constraint. Okay. So these are immobile supports. You can excite in terms of either displacement or acceleration. So for this, I am taking the displacement, and the amplitude you can give the value. And the direction you can specify with maybe any one or all the three. And the frequency functions, you can have more than one also. For each direction, you can have different functions. So for now, I'm giving for all the three, I'm giving the same function. Okay. Okay. So now the setup of FRF is done. Now we can give solve for frequency response. So right now I'm not giving for solve because we tried to take a few minutes, but that's so let us directly go and view the FRF results. So for the inputs, the base excitation what we gave, let us see. See, this is the displacement results you can see, and you can also see the range what we gave, and if in the range it is showing us what is the peak frequency, right? So these are 119 hertz, we are saying the max displacement. And we can also check on the other results as well to see where exactly the stress is at which frequency. So you can see the max peak is at 95. And you can see where exactly the max stress is occurring. And you can also plot the, since this is a FRF, so you can plot with respect to frequency how the stress values are varying. Okay, so you can see the range. So this you can save this as a PNG or PDF or TXT format. So this is how you can post process your results. So let us move on to the other type. So the other type is on the transient response. It is similar, like that was frequency approach, right? Now we need to specify the span here. So when you specify the span, suppose I have given 2 seconds, so you can see it is going till 6 modes, that is 191. So I'm going with the 2, and the other I'm making it default and evaluating all peak responses. Say okay, and you can specify the function. Here I am going with the standard. So let us say I'm going with the uniform and say, and yeah, you can see where is the excitation. Yeah, so these are the excitation points, and I'm giving here uh, in terms of acceleration, it is G. Let me take G, and you can specify here what should be the G here, and specify the directions and assign the time functions. Okay. So the setup is similar, only thing is time domain. So for this, after solve, let us see the results of it. And you can see in 2 second span, like where you are seeing the peak of displacement. And you can also plot for specific point, time versus the displacement magnitude. So the similar way we can see for the stresses as well. Okay. And yeah, the other approach was the random one. I think we have shown this in the last session, so I'm not going with the random. So let us move on to the squeak and rattle. So before going for the squeak and rattle, we need to have uh, the transient dynamics run. Okay, so we already have this run. So we can go to the squeak and rattle setup. So here we are giving reference as for the transient dynamic run, which is linked. And we need to specify gap tolerance for the rattle. Suppose I'm giving 1 mm, and for stick slip also I'm giving 1 mm. So these are basically we are defining the criteria for it. So let's say okay. And now we need to define where exactly you want to check those things, squeak and rattle. So for that, we need to specify the sampling points. So let us, like you create the connections, right? So you just need to go and add sampling points. So suppose I'm taking this as master and mate. It is similar to what you do in the for creating the connections manually. Okay. So now, so whatever the connections are there between these two, so these will be my sampling points for the squeak and rattle. Okay. Say okay. So you can see here in the setup, we have 9 sampling points. So now we are good to go for the run. So once we give that run, let us review the results. So you can see. Let's review the results here. Yes. So you can see here, if it is squeak and rattle both, then it will be red. If it is only rattle, it will be blue. Okay. So let me select all the sampling points, and you can see here it is blue. That means it is only rattle is happening here. Okay. So you can plot. Suppose I'm going with minimal gap. So minimal gap is basically least the closest normal distance between the parts and all the at all the sampling points along where the total time span when the parts are loaded. Okay. So if you can click the part, so it will show there is a minimal gap, and you can also plot maximum tangential distance. Okay, at various sampling points. So suppose I'm clicking here. So you can see relative distance, tangential distance with respect to time. So now we saw the results for this, especially we are seeing only the rattle. When I say rattle, means we have given, if you remember in the setup, we gave both the tolerance as one, right? So if you see the initial gap is zero point 0.7. So the normal gap, if the normal gap is below the open close tolerance, then the rattle occurs. Okay, so actually this is below what we gave the tolerance. Whereas for the squeak, it should be above the tolerance. So that's why we are not seeing any squeak in this. So the similar, let us move on to the thermal setup. So for setting up the thermal simulation, we need to, we'll first go with the steady state run. Okay. So for this, let me give, you can give the loads in terms of temperature or heat flux or convection and volume heat. Suppose I'm going with the temperature. So for the, suppose I'm selecting these phases and giving the temperature. So for steady state, it is actually the temperature change. Okay, I'm giving this 50. And on the other side, let me give the convection. Here I'll select this. I'll select these phases, and you need to specify the ambient temperature and what is the convective heat transfer coefficient, and say OK. So this is how you set up the thermal run. There is a steady state one. So let us review the result for this, the steady state run. You can get the temperature output, like how the temperature is flowing from one side to the other, and then the thermal flux. Okay, and you can also pick it, the points, and you can review what exactly the values of thermal flux and all. Okay, so these are the results you can see in the thermal steady state. Now you can couple this with the structural run. So for that, you need to select this, and you can create linked analysis and say structural and thermal. Okay, when you say this, it will ask which load case you want to go. Suppose I'll say thermal steady state. So you can see it has created this. and you can copy the structural loads for that. So I'll just copy this to the last load case. So now we are coupling both structural and thermal, right? And now you can solve this. So we already have these results, structural and thermal. Sorry, this, yes. So you can see in terms of displacement, stresses, and you can also see the values of, like we see what is the exact result values. So these how you can couple the structural and thermal. So this is the thermal steady state what we have done. We can do the transient thermal as well. Suppose I'm going with transient thermal. So this is also the modal based approach. So you need to specify the number of modes, what should be the time span, and what is the initial temperature. Suppose I'm taking 30, and you can evaluate all peak responses during solving. Okay. So now you can, since this is a transient, you can specify in terms of .csv, or you can go with the standard time functions. Okay. And now you can give the thermal loads. Suppose I'm giving the thermal. So this I'll give the temperature. Sorry. And yeah, here it is exactly temperature. It is not temperature change in the transient. It's taking time. Yeah. Now you can specify the, suppose you're going convection, and just select the phases, and you can specify the ambient temperature and what is the convective heat transfer coefficient, and what is the time function we defined, right? We need to refer over here and say okay. So once we have done that, now we can go for the solve. So we can just check the results of it. So this is the transient thermal results. So here you can see we have given at till 10 seconds, right? So the max peak is occurring at 9.99, and you can see the temperature change. And you can also see for the complete time span how the temperature flow is happening. Okay. And also you can see thermal flux. So this one also you can link it to the structural thermal, and yeah, here you need to specify where exactly at what time period second you want to see the results. Suppose see 5 seconds, 8 seconds, 9.9 seconds. You can have n number of it. So, okay, so we're back. Okay. So we have linked the thermal with the structural. So let us see the results. So we have taken this, given this times, right? Time history. So on that time histories, we got the results. So you can review the results as well. So like this, you can do the, you can couple the thermal simulation with the structural, or only the thermal simulations where you can see the temperature variation or temperature flow and the thermal flux flow in the structure. Okay, and yeah, so I think we have covered both thermal and dynamic runs. Just to point out, we have a couple of minutes. So we have seen the quick and rattle results before, right? Where we had, sorry, 1 and 1. Yes, yeah. We had set up with the gap tolerance, stick slip, and this thing we have set up as a 1-1, where we saw only the rattle thing. Okay, I have run one more run where I have just reduced the stick slip tolerance to 0.1. Okay, so where if you can see the results of it. So here we can see both squeak and rattle happening on this. So I'm selecting all the points. Sorry. Let me go on, say final status. So you can see, so on the initial, here we are saying the red means both the are happening at this. So this is how you can check the squeak and rattle for your simulation. Before closing it, we do have quick e-learning courses for the Simsolid, where you can learn how you can work used to the Simsolid, and we do have every month the trainings for the Simsolid introduction. So you can register and you can have a detail on the tool. Okay, so if for today's session, I think we have covered both the dynamic simulations, how can we perform, and the thermal simulation. So if you want to know more on this, so just let us know. We will get back to you on this. So thank you so much for attending this session. Thank you.